This is Hugo Aerts, and he is in the Artificial Intelligence in Medicine unit at Harvard University. And I also found out that he has got a professorship at Maastricht University in the Netherlands as well. And now we are switching gears again, and Hugo is talking about artificial intelligence in medical imaging.
All right, thank you for your attention and thank you for being here. So last talk of the day, so I hope you don't fall asleep. What I want to do in this talk, I want to talk a little bit about much more practical or much more applied than we did in the last talk. So I'm leading the AI medicine program, the AIM program at Maastricht and Brigham, and what we try to do is we try to push a lot of AI technologies into the clinic. And we're hitting a lot of barriers there and a lot of problems. And there's, I think overall in the field, there's a lot of excitement, but there's also a lot of long steps and big steps that we need to take. So in this talk, first we'll talk, let me try to get this. These are my disclosures. So first of all, talk a little bit about AI in medicine and why it's needed and what the potential is. Then we'll give you some examples in cancer imaging or actually in medical imaging in general, and also applications that could be very relevant for the mental health field. And then at the end, I want to finish with some recommendations how we think that the field can progress and should move forward. So first I want to talk about AI in medicine, right? So what we now see is that we have this cog of model development is really turning well, right? Like there's a lot of publications out there, and all of the high impact journals that are demonstrating fantastic new ways how AI can automate or even go beyond human performance in medical applications. But there's very few of these that really bridge this AI translational gap. And the main thing, so we think is, we really have to focus more efforts on validity, usability, utility, right? There's many applications that can be very useful, but are very difficult to integrate in clinical systems or will disrupt the clinic so much that they will actually not make it really into clinical translation. And of course, we do a lot of model developments, right? We also need to publish papers and write grants. But what we see in the field is really interesting how it also follows the Gartner hype cycle. There's a lot of attention. There's a lot of startups now in this space. And a few years ago, it was actually amazing at the big clinical conferences how much was said about AI. And we should stop training radiologists and pathologists and dermatologists. And that, of course, is not happening. Although we should not underestimate the long-term effects. Medicine will be completely fundamentally altered by AI. And you already see this now in fields which are maybe less interesting to publish, but think about scheduling for patients or a help desk where AI, of course, can also play a very crucial role. So what we try to do in our program, the AIM program, we try to push a lot of stuff to the clinical impact. And of course, a lot of things that we do are not ready for clinical translation. There's also a lot of projects where we think it's really interesting to translate them and even run clinical trials with them, which then actually turn out to be less useful than we thought. And of course, we can learn a lot from this. So this is a cancer care pathway, but what I want to illustrate with this is the complexity, but also all the data types that are available to us and different methods that work. So some people say, okay, we collect all of this data of these patients that we are treating. There will be a single model that rules everything. Which potentially in the future will be there, but we are now addressing this much more focused, right? So we take, for example, imaging data and we apply a certain neural network to it, or we use genomic data and we use graph-based models to improve the staging, for example. And this is what you really see is that you have these targeted solutions, and they are being pushed also and evaluated in clinical trials and clinical settings more. So all of this data is there, right? Like we're collecting more and more data of patients. The big issue with medicine is that there's not a lot of patients that actually exactly follow the same path. So we'll have a lot of different missing data, or we have a lot of data for one patient and almost no data of the other. So there's all of this chaos, and we try to make sense of this. So we spend a lot of time curating and cleaning data and making sure that our data sets are really unbiased for the future patients that will be treated. So there's a lot of issues and a lot of work that goes into making sure that this data stream is actually representative of the populations of the patients that will be treated in the future. So what I want to do is I want to give you some examples of how we how we approach this and how we think that these can be clinically translated. So the first is centered around this whole biological aging concept. And we know that some people age at different rates, right? So the biological age is not the same thing as a chronological age. And this can, of course, is also very important in mental health, but also in medicine in general, right? A 60-year-old that is very fit will likely do better and live longer and do better after treatments than, say, a 50-year-old that is very unfit. So what we try to do is we try to quantify this very difficult concept of biological age. And what is biological age? So what we said is one of our projects is that can we look at, for example, at your at a selfie, right, at a picture, a very simple picture. Can we quantify the biological age of an individual from using deep learning, from simple face photographs? And the nice thing then is, if we can do this, it is something that we can very easily integrate into clinical practice, because we can make an app that just quantifies, it takes pictures of patients before, during, and after treatment, and we can really see how is their current health changing over time. And how could this potentially be then also useful for clinical decision making? So and this is a surprisingly understudied field, because we went into this because we had the data available, and there's not that many investigations that are happening. Interestingly, the biggest field actually doing this is, for example, Facebook, that wants to know from social media profiles where a lot of people just fill in dummy birth dates and genders and all of these things. So they want to actually say, how old is this individual? What is their gender? What is their ethnicity? Because then they can do targeting advertisement for these. So there's a field out there that's actually doing this, not for a medical purpose, but for a commercial purpose or advertising purpose. So, okay, so our goal was to develop a deep learning algorithm that can accurately estimate the biological age from a face photograph. So we call this face age, the face age algorithm, where we had a certain deep learning pipeline where we first localized the face in the image, and then we did a feature extraction, and then we did a prediction, right? So in this case, Leonardo DiCaprio, right? Like, he looks like 40, but he is 45, so he has he looks younger than he is, so that's a positive thing. So we trained this on a data set that we actually manually curated, which was a lot of work, of 56,000 individuals where we had their age available. So we said, okay, these are presumed healthy individuals. We have their ages. We assume that that the noise on the output there is randomly distributed. So we are predicting their biological age and not their chronological age. And then we went to perform the clinical validation. So in over 6,000 individuals of patients that were treated for radiation oncology, so cancer patients, of two different institutions, so our own institution as well as from Maastricht, University in the Netherlands, we had these images available. And the nice thing is that in radiation, they're treating these patients almost every day. So they really want to make sure they have the right person on the table when they're treating it and they're giving radiation to that individual. So they take pictures of these individuals in a standardized fashion. So that is the nice thing about this profession, because almost no other profession in medicine actually does this. So we had all of this data available, and now we wanted to say, can we look and can we assess this biological age, and can we do many clinical experiments here with looking at lifestyle factors, looking at outcomes, of course, but also seeing if this could help, this prediction, this phase age prediction, could help humans and clinicians in better making clinical decisions, because, of course, that is our main end goal. So our main, or one of the first studies that we did is looking at lifestyle factors. So what is shown here is that your face age minus age. So if it's positive, you're looking older, and if it's negative, you're looking younger than your age. And we had a healthy reference population. So what you can see there is that on average, the majority of individuals are within 5 years of their age. right? So this is, what we also expected. There's some outliers that people look much older or much younger, but overall the average is around this. But then if we looked at the cancer data sets, we saw actually that there was a significant shift. So really demonstrating that cancer patients on average look older than a healthy population, which also is not that unexpected, right? Because you expect that these very sick individuals indeed look older than the reference. But what is also interesting, we look at smoking. So we found that actually current smokers, so people that are smoking at this moment, look significantly older than never smokers, but they also look significantly older than former smokers. And former smokers and never smokers actually was not significant, there was no statistical significance there. So it looks like that there's a reversible effect that we're actually measuring. So the moment you start smoking, you start to age more rapidly. But if you quit smoking, you also actually go back more to the mean. So there's a reversible effect that we actually can quantify and we see in these images. Also what is interesting, which was more quality control for us, we looked at BMI and we found no association. There was actually a statistical association, which always is the case with large data points, but you can clearly see that there's not a direct, we're not quantifying how heavy an individual is, so their BMI status. Then we look at prognostic performance, which is probably the most important result, where we now looked at, we make them in different categories. So we're looking at individuals in blue that are looking younger than 65, and then with decades increase to individuals that are over 85 in red, right? So, and as also, as we expected, the older you look, the worse your survival is. And this is done then in almost 5,000 individuals that we had access to. Then we also did multivariate correction, and this all stayed significant. And then we had detailed cohorts available from Harvard, where we had a lot of clinical parameters available, and we corrected for all of these. And we found that phase shifts actually complemented these models. So this really says that there's something in a simple picture, a simple selfie, about a patient's current health status that's not being quantified in the clinic using all of the tests that we do and all of the data that we're generating. So there's value in this, there's clinical value in this. And now the interesting thing will be, how do we move this forward? How do we move this forward into different clinical applications? So that whole concept of biological age and current health, we can also, of course, extend to other data types that we have available. So here is some examples of chest radiographs. And the chest radiograph is the most commonly used test in imaging test in medicine, right? Like a lot of people get it. A lot of people can also get multiple of these, even annually or for sure in their lifetime. And there's a lot of information on these scans. But the radiologists, they quantify, some radiological findings, right? But of course, there's much more information in this, right? Than is there a cancer detected or any other large anatomies. So what we try to do is we try to build a deep learning algorithm that actually can quantify how old is this individual, right? Like what is the biological age of this individual looking at this, at a simple chest X-ray. So that was the first test that we did, where we used 2 clinical trials that were prospectively collected, the PLCO and the NLST, of individuals with X-rays, and we have outcomes of these, and they were screening for cancer screening trials. And we developed their algorithms to predict their biological age. So the nice thing of what we then did is we use a relatively simple deep learning architecture to really say, only using an X-ray, how well could it predict the biological age of that individual. And in both data sets that we independently tested it on, we saw that it's very significantly stratified. So we could really identify, especially a high-risk population that we could not identify using any other sources, using simply only looking in a chest X-ray. So there is a lot of information in these chest X-rays that we can now mine and extract using deep learning and using AI that can be useful. But of course, the big question is, like, okay, nice, we can quantify a biological age from an X-ray, but what do you do with this? So one of the ways that we wanted to integrate this, or how we are now actually prospectively testing this in a clinic, is to say, if we have a chest X-ray and there's no radiological findings, right? Like there's no real radiological evidence. But we can still look at this and mine this and say, okay, but you're going to be at risk of developing lung cancer or cancer in the future. The nice thing is what we can do then is we can tunnel these individuals into lung cancer screening or other cancer prevention programs. So what we're now doing is like in the healthy population, can we identify individuals at risk for, in this case, cancer? And we built a very similar setup. We use this algorithm to test this. And indeed, we found that we could, if we would use this system, we could make our cancer screening programs much more efficient. So this is a way how we can use AI in a hospital, mine all the data that is from all the patients that is being generated, and then identify the very high-risk individuals and put these into, say, cancer prevention programs. And that is a little bit while we see this ambient or opportunistic screening, this is how we really see that AI will play a very major role. And this can also be extended to lung cancer patients, which, so there's a lot of data also that is also for confirmed cancer patients that is still important. An extension of this whole idea about ambient screening is also looking at known biomarkers. And this is something that was really surprising to us, is that, so we can use AI to also predict cardiovascular risk from a CT scan. So a CT scan is also very commonly done for screening and other reasons, for other cardiovascular diseases, for example. And many of these, and what you can see here is 3 examples of CT scans, and you're looking around here, where you can see the lungs and you can see the heart. And you can see in orange, you can see coronary calcium. So coronary calcium is the best predictor of cardiovascular events. If you have a lot of coronary calcium, you have an 86 or 87% AUC or predictive value for getting a major cardiovascular event within the next 7 years. So when you have this, we know something will go wrong. And it is druggable. So we know what to do with these individuals. We know what kind of treatment they need. We know what kind of cardiovascular prevention they can benefit from. And it is visible on almost any chest CT that's being generated in a hospital. And there's a lot of them being taken in hospitals all over the world. So we developed actually an automated system to do this. So we automatically look at a CT scan, identify it in a clinical system, identify the heart, then look at the coronary calcium, then do a risk prediction, and all of this is done automatically in under 2 seconds per scan. And again, this really allows us to just plug this into a hospital, let this machine run, analyze all the data that comes in, and 1 in 100 or 1 in 1,000 is taken out and say, this individual is at high risk for cardiovascular disease. Or what I showed you before, this individual is at high risk for cancer. And that is where AI can play a really big role. And I can tell you a lot about the training. So we use various training and tuning cohorts for this algorithm and evaluated this in various clinical cohorts to really demonstrate that this actually has clinical value. And it's really worked. And what is really interesting, one result I want to show you, is that we apply this to a lung cancer screening population. So these are cohorts of patients that are being screened for lung cancer. And we found actually that if you compare this to the lung cancer incidence or the cardiovascular incidence, that these patients actually were that we could identify high-risk patients that were at risk for cardiovascular disease, and that this population was much, much larger than the cancer population. So in using AI now, we can actually see that these screening programs are actually, lung cancer screening programs are actually more important for identifying cardiovascular disease or CVD than they are for detecting cancer. And that is something which we could never do manually. We need to do AI for this. We need AI to mine thousands and thousands and thousands of patients, which we could not do like 10 years ago. So this is really how we see it also as an accelerator of science. That also goes often wrong, so there's a lot of mistakes that we need to investigate, and there's also one of the things that we spend a lot of effort on is that what I showed you before with this COC of model developments, where research studies showing certain, demonstrating some certain value before they really can move them into the clinic. There's a lot of tests that we need to do, and a lot of these algorithms fail, and there's a lot of engineering that we also need to spend, much more engineering work than we need to do to really make these models robust. There's also other ways of where what is also an interesting problem is when, and this is lung cancer segmentation, but it's a very general problem, is that when we don't know what the ground truth really is, we have a very big issue, because the models that we train will be very specific to the individuals doing a certain task. So in this case, you can see the heart, but there's a tumor actually located between the lungs and the heart. And we need to segment the tumor and involve lymph nodes, so that tumor area, we need to segment this for certain therapy. And you can see on the left that the manual counters, the experts do not agree. And these are experts that have been doing this for like 20 years, right? They all disagree to very fundamental, very large differences. So now we generate an AI contour, and that can hopefully help to make them at least more agree, right? But we don't know what the ground truth is. So that is something that's really difficult, because the data that these AI tools are trained on will bias of course the result, and also some people will like it, but other physicians don't. So there, we use the big issues. We need to collect a lot of data. So we need to bring data in for discovery, for benchmarking. We need to bring data in from Europe, from the US, from China, where we have to capture the diversity of these patients that are being treated all around the world in that sense. And then also do a lot of very detailed end-user testing. And this end-user testing is something that is very, very time-consuming. It takes a lot of people, a lot of time, and also repeatedly over often years. And we performed these training, validation, and benchmarking experiments. And this is also very interesting, is that once we apply these, we found that in certain clinical settings, they performed great, right? The models were helping, the clinicians agreed, that was awesome. But in specific settings, they performed even worse. So we're bringing AI, a certain tool, a general tool, and we found that that actually was not very universally, we could not apply it very universally. So there's very specific clinical scenarios where this tool could be useful and others would not. And there were many mistakes that were very surprising to us in these end-user testing and clinical testing. And there's also something that we now are doing, where we really doing these caution labels, right? Like, be very cautious. This model cannot be used in specific use cases where there is a specific clinical setup, and that really reduces the value, because now instead of just using the tool and start working with it, the clinicians and the clinical teams, they need to go and have to check, okay, is one of these conditions not available, or not in this patient does not occur, and then we can use this tool. So in this way, we also discovered that actually by providing these tools to clinical teams, is that they actually would spend more time for a similar situation than before. So not all tools are, in this case, beneficial. Also, we found that if there were very rare cancer cases, which is often our problem, right? We don't have thousands and thousands of training cases. Some cases, cancer types are very rare, so we have very limited data for training. So we found that indeed the algorithms would not perform well in these rare cancer cases, so we tried to get more training in, and indeed we then also found that the performance would increase. But there's a very big fundamental problem there that we try to tackle. And indeed, also again there, we need warning labels to say, okay, if this is a very rare cancer, please do not use this algorithm in this case. What we liked actually is to see also how end-user testing. So what is how did you like this human-AI collaboration? And we found in very specific cases that we could say that it will perform better than humans alone, but also reduce the variation. And that is something that we really wanted to do. So we wanted to get to more similar solutions, that at least the treatment teams would treat the same, different treatment teams would treat the same patient in a very similar way. And of course, there was also a very big time performance. And overall, also the oncologists found it very, they found the tasks that they would be working with less challenging. So it made their life easier, which is of course also a very important aspect. And that was also not always the case. All right, so There's other ways of using imaging data or using AI in the clinic. So what we're also doing is we are using AI to probe cancer in a different way. So what you can see here are 6 examples of lung cancer patients. And what we do in the clinic is we probe that cancer, which is outlined in green. We probe that with biopsies, and we look at pathology, and we look at genomic data, right? What kind of mutations do these patients have, and what kind of histological profiles. But of course, there's also a lot of imaging information there that we try to what we can mine. And in the clinic, the only thing that we now do is we measure a maximum diameter. So we say that the tumor is 5 centimeters or 8 centimeters. But of course, AI can bring much more information, can extract automatically from these images. And that's something that is also a very big research field that we're now working on, where we're extracting, mining, this radiomics, we call this radiology and omics, and seeing how we can use this in specific use cases. And there, we are using, also a lot of CNN work, 3-dimensional CNN work, where we're throwing in like a tumor volume, and then we're trying to predict, does this patient survive the next 2 years? What is their prognosis? But also, what is the underlying mutational pattern? Will this tumor respond to certain therapies, for example? So there's a lot of research that we're doing that is demonstrating to be very valuable, where we see that there's really information in these tumor volumes that we can now extract using AI. And also that adds to clinical models, and we can also look and investigate what do they exactly look at, right? Like, why does AI think that this individual will have a poor prognosis, and can we then use this information clinically? One of the biggest fields there is, one of the most important things is in cancers trying to predict immunotherapy response. So that's something that we are also working on. It's like, how can we, from a cancer lesion, predict then using AI, apply to all of the clinical data that's available, will this patient actually respond to immunotherapy or not? And the first results are also very promising in various cancer types. The nice thing is also that we can use imaging now to track changing data over time. So patients' data being collected weekly or monthly. So we can use all of these data, and we can mine that, and AI can really track this. And that's something which humans can do very poorly, right? And it takes a lot of time. So that's something where AI can play a very major role. And we also see that there's improved performance by giving more and more information data to the AI systems to better stratify patients, and in that sense also optimize treatment decisions. And what is also very difficult there is to really say, okay, how does all this data, how is this important for underlying biological patterns? We know that cancers every cancer type is very different, so it is very difficult to make sure that this AI, what is this AI really capturing, right? Like, what kind of pattern is it capturing, and is it associated with something that we know from genomics or pathology data? And there, this is something that we work together with the Crick Institute in London, where we really look at intertumor heterogeneity and all these aspects of biology and trying to link it to it, which in a lot of ways also builds the evidence for the doctors to start using these tools, or to be confident in using these tools. All right, so we also apply a lot of foundation models and this is something which really changed the field a lot, where we really say, okay, we have all of this data now being collected in the clinic. We have all of these imaging scans and other clinical data that is in a hospital. How can we build a foundation model, and how can we then use this in very specific use cases? So also the previous talk, of course, talked about these things where we need a lot of data to learn from. We have a lot of data available, but very often in very narrow, specific applications, say, for example, in cancer, we have only very few cases available, right? So we did an investigation, and we found that for the vast majority of publications that are considered impactful in the field, that the numbers of patients that were actually included in eventually in analysis were in the hundreds maximum. So how then we can build something, like a very complex deep learning model, right? Like, that's very difficult. So the nice thing is that now with foundation models, this actually becomes feasible. So how you can think about this is that, so we use the base of the pyramid, right? Like, where we have a medical imaging foundation model where, you can think about, like, we just mine every image in a hospital. And these are unlabeled. So you have an image in and an image out, right? Like, and then you create a foundation model that just learns what kind of representation of images are actually exist in a CT, PET, or MRI scan, for example. So that's then a foundation. So this takes a lot of time, a lot of energy, a lot of GPU power, a lot of also coding time. And then, but once you have it, you can now then go to the next base, where you can say, okay, now, for example, let's do brain segmentation, right? Like we have an MRI, we want to segment a different region of the brain. But now what you do is you just present it only with masked MRI images. So this is a more use case specific foundation model or unsupervised training. Where, again, there's no labels, there's no human that annotated anything. And then in the tip of the pyramid is actually where we have limited, smaller data sets that are actually fully annotated by humans and labeled. So the nice thing now is that with very few training cases, and sometimes these are in the tens of hundreds, but not in the thousands or tens of thousands, we can get very high-performing models that are built on, maybe a million different scans that were from old medical imaging data that was available. And that's now really the power of foundation models in medical imaging, but in various fields of medicine are really transforming the field, where we can indeed apply now, we can develop solutions in small data sets and with high performance. So this is one example that we did where we applied it, where we trained it on different lesions, a foundation model, we built it, and then we did a certain technical and clinical validation studies of these foundation models. And I apologize a little for all the plots, but what is really interesting there is that especially in these limited data scenarios, so where you only have a few training samples available, you saw that these foundation models performed significantly better than the, standard state-of-the-art SOTA methods that were used before. So that is something where we expect that actually a lot more studies will come out with these smaller data sets simply because they were built and used foundation models and therefore, but still yielded high performance. All right, so now I want to switch to actually one of the main problems that we see in the field. And this is actually a paper that came out a few years ago in Science, which I really enjoy reading. And it's about reproducibility in the field. And so there's numerous publications about AI in medicine and all the top journals that are being published. But there is a very big reproducibility crisis. And this is something that a lot of people underestimate. They underestimate how difficult it is to reproduce studies, and also the big need and why this is a bad thing in science in general. Because if something is not reproducible, we cannot really build on this for the future, and even the wrong things get published. So we steer the field in the wrong directions. And what they did here, they really show that there's only very few papers and authors that are actually sharing code, sharing data, sharing even a detailed enough methods description for others to actually reproduce your results. So we wrote actually a response with a big team of people about transparency, reproducibility, and AI. And it is really amazing that in other fields like genomics and bioinformatics, this is all already sorted out, right? Like 10 to 15 years ago, the whole field came together, they defined standards and guidelines, and they now, if you do not share your code, if you do not share your methods, if you don't share your, the full pipeline, even, like low impact factor journals won't even publish you. But that is very interesting to see how actually the medical AI field is actually replicating all of these mistakes, and the vast majority of papers out there today are still not reproducible. And there's likely also a lot of papers out there that are not correct in that sense. So this is a thing that we just have to realize that it's good to share, and it's a good thing to make these tools available. But a big thing there is also, again, back to the medical imaging field. It is very difficult for scientists to share their tools to the community, because just sharing a GitHub repository or like a code repository, that is not enough. We need to do more. And but if the tools are not available, how do we help them? So that's something that we work together on. This is actually the computational reproducibility because AI is so complex, we need more and greater transparency, because very small details can matter a lot. It is think about a biology experiment. You need to know exactly which agents were used and how long and everything. But that in AI, that's not the case, that we describe in that level of detail. So we need to go there. So one thing that we try to do is with a bigger NCI effort, where we try to give investigators the tools actually to share these methods to the public. And that's something that is now, we took a lot of time actually to define what is the standard and what is the, not saying in a guideline, but actually in, this is how it should look like, and helping then investigators to share their tools. And this is something that we are now working on hard. So if you are interested, we call it mhub.ai. And we are trying now to integrate these model solutions into various platforms that are widely used in imaging and also in neuroimaging a lot, as well as platform-based online platform, cloud-based solutions like the IDC. And what we also do is we provide a lot of documentation, much more than is normally that is available. So we described in length how every model works, what is the training data, how it's tested, how it's validated. And this is something which is a lot for a lot of people to ask, but it makes it so much easier for other people to actually see, is this model really interesting to me or not? And that is something that we also hope that more and more people will adopt. All right. That was it, and thank you for your attention.
Wow, the future of medicine. So, there are still a few individuals around here with stamina. So, I can see Mayank has got a question.
Yeah, this is absolutely amazing. So I wonder, like, for example, there might be, apart from the images, in which there is clearly, you mind, amazing amount of information, there may be other sets of information which is not in the images, for example, in the genome of the person, which has a big impact. So one clear example might be face age. Some people of some nationalities, they just look young forever. Other people don't look. So have you seen that for example, do your algorithms remain insensitive to these systematic variations which are due to factors beyond the images? For example, in case of face, does it accurately predict, regardless of nationality, the true age?
Yeah, so is this on? Does it work? Sorry. Oh, yeah, this works. So with face age, that was is one of our big limitations, is that we had two cohorts, one from the Netherlands, one from Boston, which are 85% white.
Yeah.
Right? We validated this in the UTK dataset, which is a dataset that actually had more ethnicities, and we looked at the error for predicting age, and it was very similar. So it looks like it was a similar, but we do not know. The good thing is for the training data, it was much more diverse. But we still need to prove it also works in patients that from other ethnicities. And that's something that we for sure need to investigate. And that is actually, that is something that we know is a very big problem with this. Going back to your genomic data. So, some people indeed always look young, but in some ways it is also that we really more quantify the current health status. And the biggest, and this is follow-up experiments that we're now doing, is actually in the change. So if you, look like a 45-year-old, if you're 45 and you look like a 45-year-old, but then 2 weeks later you look like a 50-year-old, then there's something, you're more frail. Something happened. And this current health status, the delta, will be much more important, we think. And that's something where the initial is actually maybe a nice baseline, but the change will actually be something that we need to quantify. But the big issue there is that, how does it with different lighting, right? Or different backgrounds, and how does it work with, enhancements, right? Like if you get some surgery or some...
Botox.
Botox, yeah, exactly. Well,
forever young.
Yeah, forever young. So it is there are a lot of problems that we need to solve in this, for sure. Yeah. But it is something that is in some ways underlooked. And I even wonder now, I do not know, but is Facebook doing this already and saying this individual is actually aging more rapidly, so they do worse than their peers? Maybe something is wrong. Let's advertise more drugs to them. I do not know, right? Like that's maybe something that already happens. Yeah. But it is something that there's a lot of data there that we can potentially mine, and we should for sure look into it.
Super, thank you.
I have a very different question, but related with what you say in the future. Do you think that one day artificial intelligence and medicine can find a solution for immortality?
Oh, for what?
Immortality.
Oh, wow, that is a big question. So, yeah, I'm not an expert in that, so I do not know. But that is not something that I think though that the AI will really have a huge impact in medicine. We'll make it cheaper, better, in many different aspects, and there will be less mistakes, and that's something where I think a lot of things come in that we just, medical errors, which is a huge problem, right? Like the medical errors made in every hospital almost daily, right? Like, and some are very small, or the vast majority are small, but some are very major. That is something where AI and monitoring can really play a huge role as well. But I'm not an expert, and so I cannot help you really with that question. If are we going to live forever? I do not know. I'm not a biologist in that, but if AI will probably live on forever. I'm not sure if we will.
Can I ask a second question that is also related, but further in the future? I read a lot of documents from well-known people, and they were talking about if it's not the human who can be immortal, it could be also the soul of the human who can be immortal through artificial intelligence. Have you ever think about this? And what do you think?
Unfortunately, also I'm not a very big expert. So is the idea then that that AI would take your soul and then the AI lives on forever, but your biological being just dies off? Is that a little bit I do not know anything about it, but I think it's going to be very hard to do.
Thank you for your answer.
Of course.
Stephanie.
A few questions here. What are your thoughts on integrating MedPalm into clinical practice, since it utilizes algorithms or diagnostic and therapeutic purposes increasingly better than clinicians? What does this mean for the future of our medical profession?
Yeah, so that is a question that comes up a lot, right? Like, so general statement, and a lot of people have made this, but I also really believe this. A doctor with AI will always do, or will likely do better than a doctor without AI, right? So we will, and more of these tools get integrated into the clinic in various fields, right? In radiology, pathology, dermatology, like across the board. We have to be very careful though, and that's also a little bit the gap of the AI translational gap I showed you before, is that we think that some of these tools are very useful, but often if really with thorough clinical investigations, they turn out not to be that useful. So we have to be very, very careful, and there's these obvious things that humans rely. I have a co-pilot, so why I'm just pay less attention, right? Which is a very bad thing, because then the AI could have missed something, and then the human also misses it. So over reliance. So these are the obvious things, but also it could be that we're biasing the populations, that we are including more patients than we did before, and we're making different clinical decisions. So it is very, very important to very rigorously validate this, and that's the only thing that I'm a little bit afraid of, is that some of these tools are being introduced too early, and then patients get hurt by this. But yes, it is something that for sure will change the profession. The only question is how long it will take.
Great, thank you. Have you tried to identify biological age from X-rays or internal organs? How different is the face from other parts of the body? Yeah,
that's also a great question. So a face age, why we like that concept, is it's something that we can very easily get. We can take a selfie or picture of anybody, right? Like, and we can make an app that somebody does this daily, and there could even be an app that is like a fitness app, and they can say, how old do I look today, and like this, and then they can see their progression. So that is the nice thing about face age. We know very easily we can get an idea about the current health status of that individual. An X-ray, of course, contains much more valuable information. We're looking at the internal aging, we can have a view of your internal organs and their current state. So indeed, we also see that using these X-rays and applying the AI models to these, that we can have much better models for predicting survival, for predicting outcomes. There's much more information in this simply. And again, we have more with the CT scan, because the CT scan is much more valuable again than an X-ray. So there's different levels of data we can collect and different ways of using this. But of course, we cannot make an X-ray of everybody, right? We cannot give a radiation dose to everybody every year. We could potentially, it's not that much, but it's going to be very costly. So yes, there's an enormous value in these X-rays and CTs and other imaging data that we can now extract and mine, but other approaches, like phase age, could also be useful in populations that are more healthy and don't go to the hospital very often, like alert systems. So we can very early on, we can identify something is wrong with that individual, maybe they have cancer, cardiovascular disease, and steer them into prevention programs.
Okay, good, thank you. What is the FDA's position in approving AI algorithms in the clinic?
So the FDA has a little bit, I really like what they did. So it all depends on risk. So if there is very low risk, then it's relatively easy to integrate. So say there's a human that can always check the output and can control this and make sure that actually what the AI did is correct, then it's relatively easy with a 510K, like a certain regulatory path, to get these tools into the clinic. The big issue is going to be where in certain applications where we have to trust the AI blindly, right? So say, for example, we find a lung nodule in the lungs. Is this benign, which means that this patient probably lives on forever or a long time, or not forever, or it's malignant and this patient needs surgery very soon in cancer treatment, otherwise they're going to be dead in half a year, right? Like, so there's a very crucial decision. So, but there are, and Google also did built some tools to detect this and discriminate between these two. But then if there's a mistake, it's going to be a huge problem. And a human does not know. They look the same to us. So we need to trust the AI blindly. And for these kind of applications, we need to have a much rigorously quality control, assure that that these imaging devices keep on, these methods keep on working also in an imaging device in 10 years. And that's a much more detailed and much more rigorous process, of course, what we expect. So some tools can be very easily integrated with zero or very low amounts of regulatory oversight. Other ones will be very hard to get in.
Okay, thank you. If the purpose is to predict adverse health outcomes, why not train on those outcomes directly rather than indirectly using facial appearance age as a proxy? Is this because more direct data isn't available?
So yes, adverse events, of course, is a big thing. Indeed, one is correct that we have much more images with their ages or survival, for example, than we have very detailed adverse events. The adverse events is also something that's very difficult to collect in clinical environments. Not the only, but it's done very well by pharma. So pharma, they know exactly what their patients, they give drugs to patients and they know exactly what happened to them because they need to know and they need also to get FDA approval. This in clinical settings is much more harder. So training against other surrogates is something that we can use and then because the data is available.
Thank you. Those are all the questions from the virtual side. Thank you.
Okay, thank you very much. And we are exactly on time. That's fantastic. So first of all, I would like to thank Hugo again. But we should also thank our other speakers. Some of them have already left, as I mentioned earlier, because they have further commitments. So for today, I want to finish this, and I really say that I have learned a hell of a lot just by listening to these talks and how wide a range we have covered. So I think this is a really successful symposium. So thank you for everyone who participated.